Hello everyone. Today I wanted to change topic a little bit. So we've been talking about scalability in blockchains, but we haven't yet talked about layer 2 or Lightning Network so far. Right, so if you recall from the previous course, we had discussed about off-chain payments using Lightning Network. So this was a clever idea proposed by a couple of groups actually independently. But the idea is that you don't record your transactions on the blockchain. What you do is you have a smart contract between various parties, let's say A and B, and you can create what is called a bidirectional payment channel. So initially there is a funding transaction which creates this channel, and for example there could be 1.5 BTC here and let's say 0.5 BTC here. So this is the amount they sort of bring to the smart contract initially, and subsequent to this you can have any number of transactions which are not recorded on the blockchain, right? So the initial funding transaction is on the blockchain, but then let's say this person A pays B 0.1, so the balances get updated, right? Maybe he pays 0.2 next time. B pays 0.3, let's say. So these are all off-chain. And this gives a huge amount of scalability because none of this is recorded on the blockchain, right? So of course if you want to terminate this particular channel, you could close the channel, so both get their money. Right, so this is what we looked at in the previous course. Right, this is how an individual payment channel works, and the smart contracts for this, essentially for this payout transaction, are updated every time there is a new payment. Right? So this is fine. This is about a single channel, but we said we can extend this to a network. Let's say there is 0.2, 0.8, right? So it can be any network, right? Any topology, and essentially between any pair of nodes you have a bidirectional payment channel with some amount of money initially deposited in the channel. So if you want to make a payment across multiple channels, suppose A doesn't have a direct payment channel with D, he could use this particular path, or there could be another path, for example going this way. Right? You can go this way or this way and so on, and make a payment. So this looks a little bit like a network, but of course it's different from a typical computer network, because what you have in a typical computer network, if you're sending a data packet, let's say, across a network, the packet is processed at every node. There's some time for that processing, and then there is some link speed which limits the speed at which your packet can be sent out on this link, right? That's how a computer network works. Here there is something like a link capacity, in the sense that you can't send more than 0.2 Bitcoin this way on this channel, and you can't send more than 0.8 this way, right? And as the balances get updated, the limit on what you can push in any direction keeps getting changed. So it's sort of like a weird type of computer network where the link capacity sort of like changes, right? And if you think of this as being, let's say, two links, right? Suppose I think of the link in this direction and a link in this direction. This is limited by 0.2 and this is limited by 0.8, right? And if the balances get updated, then some of this can be shifted here and so on, right? So what can happen in practice is that when you're trying a particular path to make a payment, you might find that that particular path does not have enough capacity, you can say, or enough of a balance to send the amount that you want to send, right? So suppose I want to send, let's say A wants to send D 0.3, then it will not be able to go along this path because it will hit the bottleneck over here, because only 0.2 can be sent out from this end, right? But what if I send less than 0.2? Is it always going to work? And the answer is not really. So suppose this becomes, let's say there's a payment here of, let's say, 0.15. So what becomes the balance here? It is 0.05 and 0.95 becomes the balance. Now if I try to pay 0.1 from A to D, it will fail along this path, right? Because the balance is reduced over here. Okay. So just let's write down to summarize what we have discussed. So one issue is that total amount which can be sent on a path varies over time. Depending on the balances. On the links of that path. Right? So this is one issue. Another practical issue which comes up in Lightning Network. So this is true for any payment channel network. So particularly true to the Lightning Network is that you don't know the current balance. So this is not public knowledge. And you might wonder why. So it really has to do with privacy. So suppose everybody was aware of, let's say, the balances here in real time, let's say A made a payment of 0.1 to D, anybody would clearly be able to see that 0.1 was sent along a particular path, because you'd see the balances changing at roughly the same time by almost the same amount, 0.1, on all these links. So anybody who's, if this is public knowledge, anybody will know that A has paid D 0.1. But we don't want that information to go out, because we wanted some amount of anonymity in Lightning Network. So we said we use things like onion routing, for example, right? So I think I mentioned that in the earlier course, where each link doesn't know more about the payment than what happens along its own links, right? I mean, so let's say B knows that it got money from A and it paid to C. It doesn't know who C has paid, right? So each node only knows about the previous node and the next node in the way the Lightning Network is set up, okay, using the onion routing method, right? So this is an issue. If the current balances are unknown, then what do you know? Do you even know these initial amounts? Okay. And well, you can think about it. So this initial amount is there in the funding transactions which are there on the blockchain, right? So that information is typically known in the Lightning Network. So the initial balances are known. So suppose A wants to pay D, what does it know and how does it make the payment? Okay. So in the Lightning Network, A would typically have information about the topology of the network. Even if there are, let's say, thousands of nodes, it would know the graph of the network. It would know the initial balances on the different links, but not much more than that. It doesn't know what is the latest balance, whether it is 1.4, 0.6 or whatever it is, right? I mean, of course, here A would know for this particular link, but it would not know much about links further away, right? So how should A decide which path to use? And that is the problem of routing in payment channel networks like Lightning Network. Okay, so a naive method would be what? Use the shortest path. Okay. So in this particular case, the shortest path is this one, right? And this one is longer. So A might want to try out this path. But so it would have to send information from here to here, right? Updating the smart contracts and so on. It would have to set up the HTLCs which we looked at in the last class. Right? And it may happen that one of the nodes does not have the required balance. And in that particular case, the attempt would fail. Okay, so it would look at the topology, find the shortest path, but of course you might think that maybe the shortest path will not allow the payment, right? If the payment value is too high, and let's say that the initial values on that path are insufficient, then unnecessarily we would try it out, right? So let's say use the shortest path whose initial balances allow the payment. So for example, a payment of 0.1 from A to D would go through with these initial balances, right? And this is the shortest path, so I'll try on this path. But what may happen is that the balances have changed and it may fail. Okay? Also, it may not be that that actually this balance has been updated here. There may be some balance temporarily unavailable because of this locking. We you know that L in HTLC stands for locked. So initially you have to lock the amount and then it is released after, let's say, D releases the secret, right? And in the Lightning Network, of course, D releases the secret, but there are other methods like the Radian method used in Ethereum where the sender releases the secret. Okay? Anyway, for whatever reason, either because the amount was transferred from one end to the other or that it was temporarily blocked, you may not be able to make a payment. Okay? And in which case, the attempt for the payment may fail. So what should we do now? Now if the payment fails, should we give up? So obviously I mean such failure should be expected. So we need to do something else. Okay? So what do we do now? And that makes the question more interesting. Okay. So suppose this fails, but maybe there is some other path, let's say. Okay, so there are clearly many different options over here, right? And if you know where the failure occurred, let's say the failure occurred on BC, then clearly you shouldn't try ABCFD because again BC would fail. Maybe you could try this path, right? So we could try that. So we would try another path. Okay. And exclude, let's say, a link where there wasn't enough let's say capacity. Really what I mean here is balances. Okay. And so if you can find a path from the source to the destination which doesn't include any of the links, then that of course satisfies this, right? And that too is fine. So let's say entirely new path. Let's say except for the source and destination. So this is an issue that we face, and the question is how long are we going to do this? So the first path we try out fails, the second path might also fail, And what happens then? And in fact, it takes some time for you to find out that the path has failed, because you're trying to send messages from one node to the next and so on, right? There's a lot of back and forth sort of discussion between every particular node, right? So it takes some time, and you keep getting, let's say, timeouts or whatever, right? The payment doesn't get through, or right, you have to keep trying, and finally the transaction itself might fail. So the transaction may have a timeout. So after this, the transaction fails. So this can happen in the Lightning Network. So what we look at, what a lot of the research papers look at, is something called a success ratio. Which is a number of successful transactions divided by number of transactions, right? And here we are assuming so we assume that every time suppose a transaction fails and you try to redo the transaction, then it's a new transaction. So retry of a failed transaction is a new transaction. Okay. So just to be clear here, you can have many attempts for the same transaction. You can try different paths and whatnot. You can do that any number of times, and if you succeed before the timeout, then it's a successful transaction. But if the timeout expires, then you failed, and right. So you could retry. You can just give up trying to do the transaction, or you can retry the failed transaction. But if you retry, then it is counted as a second transaction. Okay? So that is how the success ratio is calculated, right? And if you have a good routing scheme, then your success ratio will be higher. Okay? So we want the success ratio to be high. So if it's close to 1, then we are in business. Okay. So what should we do to make the success ratio higher? And it turns out that this reminds people of traditional computer networks. Of course, this is not exactly a computer network with a router and where you have a certain capacity and so on. Okay, but you can think of it as a sort of a network. And in networks too, we want to find paths, right? We want to find a path over which you can send data from one end to the other, right? And so a lot of research work happened in the computer networks field over a period of 25 years even, or even more than that, right? A lot of clever ideas for routing information and so on, right? So is there a way for us to sort of find out which paths work, right? So those are things that we can ponder about. So can we find paths in advance let's say which have enough balances. Okay. Um, then the next question that we might ask is, can we rebalance channels? So suppose, let's say the money goes from one point to the other. Let's say it's 0.2 and 0.8, and it becomes 0, 2 and 1.0. Now nothing can be sent from B to C, but can I push some amount of the money this way in order to rebalance it? So can I make it 0.5, 0.5? So is this even possible? And you might wonder how is it possible, because B has paid some amount to C. So basically we are asking C to pay some, let's say 0.5 to B, which seems unfair to C. I mean, just to keep the balances sort of even on both sides so that payments keep continuing, why should C give up its hard-earned Bitcoin, right, and push 0.5 over here? That doesn't make a lot of sense, right? But it does. Could it be done in practice? And if you think about it, there may be situations where this is possible. So let's say we have A here and G here, and let's say F, and let's say we have 0.5, 0.5, 1.2, 1.2, let's say so suppose all the balances are what's shown over here, and except that now we have 0.0 and 1.0 here. Now can C push 0.5 without losing money? And really that's what we want, right? C should be fine with pushing 0.5 this way, provided overall he doesn't lose money. So if he gets 0.5 from somewhere else, then that's fine, right? So in some circular path like this, we can just rotate the money so that nobody actually loses any amount, right? So C could get 0.5, right? He can push 0.5 here, and we can push 0.5 from here to here, and so on. Right, and we can push 0.5 finally, so that this particular channel becomes balanced, right? So it's fine. I mean, this sort of a thing is possible. Of course, you might say, what about transaction fees? But of course, we are neglecting that in this discussion. I mean, so nobody is actually losing any money over here. So maybe they might do it for free, because there's no actual payment using the Lightning Network. It's sort of just between people sort of who are sort of friends maybe in this circle, and they're just exchanging money, right? Anyway, whatever it is, there could be a transaction fee or there may not be a transaction fee, right? But this is possible to make payment in this circular path so that nobody loses money overall. What happens over here? So you see that 0.5 has been pushed over here everywhere along this path, and we see that this becomes unbalanced now. to balance this channel we pushed 0.5 around and we unbalanced this particular channel, right? So that becomes an issue too, right? But this rebalancing is an idea which could potentially be used, okay, in order to reduce the chances, let's say, of somebody choosing a particular path which doesn't have enough balance. Okay, so there's no clear way of doing everything correctly, because maybe for a certain payment 1.0 and 0 is actually the best thing. For example, if a payment was going this direction, somebody wanted to pay, let's say, 0.8 this way, this is fine, 1.0, 0.0, whereas if it was 0.5 and somebody tried to make a payment, then this link would fail, right? So we are sort of assuming that a balanced channel is what we want, and that may make a lot of sense if the payments are small, right? But if there's a big payment, then you never know, maybe an unbalanced channel is the right thing. Okay, so lots of different ideas have been proposed for routing in payment channel networks, and I wanted to consider an idea today which is called Spider. So Spider was a method proposed in NSDI 2020, right? And it's proposed by a number of people. One of the authors is, if any of you are chess fans, right? I think this is how you spell his name. Last name is Negi. So he several years back he was one of the top players in India, right? And he became a grandmaster, I think, at 15, which was very young. I mean, at that time it was probably he might have been the youngest grandmaster from India. But now I think, of course, we have 14-year-olds who become grandmasters and so on. But he had a bright future in chess, I'm sure. But he decided to go back to study, and he went to US, to Stanford, and I think he's now at MIT. So he's one of the co-authors, right? And I believe the first author is Vibha Lakshmi. Let's talk about some of the key ideas in this Spider paper. So this whole group of people, it's a very long list of authors on this paper. Many of them are from the computer networks background, right? So they are thinking like networking folks, and they wanted to reuse some ideas and, of course, modify them appropriately to solve this particular problem. And most of you have studied computer networks, so you will know that in computer networks you don't send a full file as one packet. You don't send it in one shot. You break it up into smaller pieces and you send it out, right? And of course there's various reasons that is done. There are various networking reasons why you want to break up a large file into smaller packets. But what happens is that these individual packets flow through the network. Some of them may actually take different paths. Okay? It's possible if, let's say, but usually it would follow the same path. But it could happen that somewhere in between, let's say, the route changes even while you're downloading a file. So some packets might take a slightly different path. That may happen. Okay? So why would you want to think about it in that fashion? So what they're trying to do is they're going to consider a transaction. So this is a payment channel network and this is the internet. We're trying to make a comparison. So here you have a transaction, and here let's say you have a file. So here you want to push the transaction across the network, here you want to push a file over the network. So here, what do we have here? There's a file over here. We have a transport layer, and we also have packets. So we're just dividing the file into smaller parts. Of course, in computer networks we use different terms like segment, or depending on the networking layer you're talking about, segment or frame and so on. Okay, but I'll just use the term packets. They have the clever idea of trying to think of a transaction as a file. Okay, and so how can you think of it? Because here there's actually more data to be sent. So here the size is in terms of the data and megabytes and so on, but in the Lightning Network a transaction actually has the same amount of data. I mean, whatever, let's say there is just a smart contract which has to be updated. So it's not like you have megabytes or gigabytes of a transaction, right? It's some small amount of information which has to be sent across. But the size here refers to the amount that you want to push across. So if the transaction involves a large amount, it's like having a large size file. Okay? And it does make sense because the capacity of links in the payment channel network is really how much money you have deposited in that particular smart contract, okay, which manages the particular link. Okay? And if you send a very large transaction and the balances are small, it's going to fail. Anyway, but what they want to do here is that they also want to have something like a transport protocol, and they want to have something like packets over here. So why do something like this? Well, if you look at this network that we have over here, so suppose I want to make a payment of, let's say, I want to make a payment of 1 BTC from here to here. Let's say that I have 0.9 here. Let's say I do whatever. So in the earlier methods that we considered, what would we have done? We would have chosen the shortest path. We would have tried to send 1 BTC and failed over here. Then we would have tried some other path. We would have, let's say, tried this path. We would have again failed. Okay, so the naive methods that we tried out earlier would say that you cannot make a payment from A to D of 1 BTC. But if you think about it, we can actually do it. If I send 0.2 along this path and 0.8 along this path, that would be possible. Right? There's nothing to stop it. Of course, I'm assuming that we have these initial balances everywhere. But if these were the balances, indeed I could send, but I would have to split up my transaction into two amounts. Right? I couldn't send it all as one shot. A payment of 1.0 would be impossible in one shot, but I could split it up into two parts and manage to get it. So that's the intuition of these packets. I will not send it together, I would split it up into smaller transactions and make them individually. So So what are these? These are smaller transactions. Okay, and the total amount is that of the original transaction. Just like here you had the individual packets, overall when you put them together you get the original file. Here effectively you have paid the amount of this transaction, but you've done it through many smaller transactions. So what is their idea here? Since I'm sending out these smaller transactions, they are the chances of them hitting a channel which is doesn't have enough balance are lower. It's a smaller amount in transactions, there's less chance of a failure. Secondly, I can try the smaller payments simultaneously. I don't have to try on one path and if that fails then I have to try on the other path. For example, in the earlier what I just talked about, the earlier example, I could simultaneously try on two paths, 0.2 on one and 0.8 on the other. Okay? Can simultaneously send multiple smaller transactions. Right? So this is good. Maybe one of them fails and one of them gets through, or you can even send out 5 packets, for example. Okay, so you can simultaneously send multiple transactions on different paths, or even on the same path you can try it out, right? Okay, so this is a clever idea. Then also, as I discussed earlier, that you can have a transport protocol. Let's say we can adaptively change the rate at which we send transactions. And now to understand Spider, we need to recap a few networking concepts. One of them is active queue management. So what is this? Well, if you think of a computer network where you have various routers, normally these routers have some queues where you can buffer incoming packets, and of course they try to empty out these queues as soon as possible onto the output links, right? So each of these is a router, and these are links coming into the routers. So what does active queue management do? So if we zoom into one of these queues, what active queue management wants to do is it wants to give some feedback to the TCP, the transport protocol, that there is congestion over here. So what typically these AQM schemes would do, they would mark packets. So they would set some bit, let's say, in some header in the packet, right? So they mark packets to indicate congestion. So it could be just setting one bit in some header, right? So a simple way to do this is to sort of say that if a packet is delayed in a router more than a particular, or if it's waiting in the queue for a certain amount of time, then you mark the packet, right? And how this could be implemented is that when a packet enters a queue, the queue is larger than a certain threshold, then you can mark the packet, right? So the packets go all the way to the destination, right? And this information can be fed back to the source in terms via some acknowledgement packets. So let's say you have data going here. This is TCP data, and then you have TCP acknowledgements. And the TCP acknowledgements could resend back to the source what these bits were in the packet, right? So you would want to give explicit feedback about congestion to the transport layer, the TCP layer, just by marking these particular packets, right? Okay, so this is one idea which the Spider, the people who have developed Spider, they want to reuse this idea in their method, right? A second thing is TCP congestion control. So what does one do in TCP congestion control? One has something called a window. So TCP congestion window. And that is made to vary over time. So typically what is done is you have a slow start, you have a very fast exponential increase followed by an additive increase, right? And then when you have a packet loss, you decrease your window size by half and whatever, right? So it's a complicated scheme used by TCP, but the idea is that if the network is congested, which you can detect either by a packet loss, or if you have some explicit information coming back about packets being marked, you could decrease the window size. So when you know about congestion, whether it is a packet loss detected, right, or whatever, it could be due to timeout or whatever, right? Or packets are marked by routers, so by active queue management. Right? You can decrease the window size, and the idea is that you don't want to pump too many packets into the network. If the network is congested, you want to send out fewer packets, right? And just to recap, how is the TCP congestion window really related to how much data you can send out? So your congestion window is equal to the total bytes which are in flight. So by in flight I mean they have not been acknowledged as yet. Okay, so the window is larger, then I can push out more data into the network, right? And this limits how much I can push out. I can't push out more than the congestion window, right? So these are sort of ideas from networking, and some of them are reused over here in Spider, because really the folks and the authors are essentially networking people. Okay, so how are they going to use this? So first of all, there is something called a spider router. So we want to reuse these ideas, but in the context of a payment channel network. So this is any payment channel network node which is intermediate, right? So I may have ABCD. This is a payment channel network. So any of these, you can think of them as being spider routers. Okay, and what are these going to do? So first of all, we said we are going to divide a large transaction into a number of smaller transactions, right? And these are going to be sent out. So each of them is going to be called a packet. So this is let's say a PCN transaction of a small amount. Okay. So these are going to go, at let's say this is the network looks like this. So at any of these links, you will have a queue of pending transactions. So I'm just going to call them packets because I've said a packet is essentially a PCN transaction over here. Right? So let's say A is sending out a lot of packets. There could be other people too, right? There could be, let's say, right? So all these people A, F, G could be sending packets to B, and maybe they are going over this link. So those would be put in this queue, and they would be processed as soon as possible. Okay, so what does it mean to process? Well, I mean, B would have to contact C and say that I want to set up an HTLC corresponding to such and such a transaction. Okay, so we are abstracting out the fine details of what exactly happens in setting up a path, and that the destination has to send a secret back to the source and that sort of thing. So we are leaving out those details, and we are trying to think of this as a computer network. So once I send out a packet, what is going to happen? Essentially what is going to happen is that some amount gets locked over here, right, on this particular channel. So suppose there is an amount B here and amount C over here. So every time one particular transaction is sent out, this B is temporarily B is set to B minus whatever the transaction amount is, and this much is locked, right? So the balance is sort of become this. And of course, once the entire path is set up and D sends back the secret along this path, then these values actually get updated, right? So this is sort of what is tentatively happening, right? These values are really updated after the whole procedure is completed. But of course, for some time this is actually locked, right? Because it could be that the transaction doesn't get through, in which case B and C don't change, right? What would normally happen in the Lightning Network is that if there is not enough balance, what would happen is that B would immediately reject the transaction, right? And there would be a message going back to the source that I cannot complete this transaction, right? Okay. But what Spider allows is that it allows B to keep transactions pending in a queue even if there isn't enough balance. Okay, so let's write this here. Since there is not enough balance, okay, so this is where we are differing a little bit from the Lightning Network. In the Lightning Network, there is no such thing as a pending queue and so on. If there is enough balance, you would lock the amount and to send off messages along the rest of the path. Here you would keep the transaction pending in the queue over there. Okay. And how are we going to use this idea? Well, we're going to use the idea of active queue management. So if a packet is in a queue for greater than 75 milliseconds, some threshold which they suggest to be 75 milliseconds, then you mark the packet. Okay, so this is a sign of congestion. Okay. So what happens is after some time, let's say there is some channel balance, right, available, and then these transactions are actually, or these packets are processed and sent over this link. So why would there be a balance coming up? I mean, because you might say that B is decreasing, right? This value keeps decreasing and this is increasing, and maybe this has already hit 0, and then all these transactions are just pending over here, right? So how would this get back above 0? Well, because here too, at this particular place, we have pending transactions, and what happens is that transactions going in this direction are going to push the balance from C to B, right? And that is going to allow these transactions through. So this is different from a networking paradigm where there's no such thing as a balance on each end and it keeps getting pushed here and here, right? But as transactions go through from here, this decreases and this increases, and the opposite happens when transactions go this way, right? So if these transactions are pending over here because of 0 balance here, transactions going in the opposite direction will make this positive again and decrease the amount of it, and then transactions can be emptied here, right? So this is what is going to happen, and these marked packets reach the destination, and then some feedback is given to the source that this path is actually congested, right? So just like in networking, the destination is going to tell the source. So suppose, let's say that A is sending to D many packets. So D informs A if packets are marked. And the question is, how does D inform A that the packets are marked? Well, it doesn't have to send the information over necessarily. I mean, it could directly send information to A, because this is a payment channel network graph which I've shown over here, but A and D can directly communicate over the internet. That is not an issue at all. So that information could be sent from D to A, right? Or that information could be embedded within the PCN protocol itself. That too could be done, right? But then you would have to send it over these nodes, which which may not be required at all. D can directly send a TCP, a real internet packet all the way to A, just saying that there is congestion along this path. Okay, so this is going to be used by A, in order to reduce the data rate at which it is sending on a particular path. Okay, so these routers are going to push as much information, as much transactions along various links. Okay, but at the same time, there is a transport layer which is going to use information about congestion in order to take some action, which we'll discuss next. Okay, and the way that we convey that congestion is there is that we actually mark packets as we send them through. Okay. So there is one other thing. So the queuing discipline that is used and of course they tried out many things in the paper, but they recommend last in first out. So the queuing discipline recommended by the authors is last in first out. So what exactly is last in first out? Suppose I have a queue. Normally we do first in first out, which means the first packet which goes in goes to the is really here at the head, and subsequent packets are kept behind it, and we serve the packet which is at the head of the queue. That is first in first out. But last in first out means that the last packet which goes in is the first one which is sent out from the queue. So the last packet in is the first packet sent out. And from all the queuing disciplines that the authors tested out, they found that this is better. And the reason is that we said that a transaction has a timeout. Not just this individual packet transactions, but the larger transaction has a timeout. And ideally you want to send packets so that you don't actually hit that timeout. And what they found is that if you sort of do a first in first out discipline, where the first packet which entered the queue is the one which is serviced whenever there is any ability to service the queue, okay, then what you will end up doing is that all the packets will be delayed excessively, and you might hit too many timeouts for the transactions. So they said better to use last in first out, so that maybe it's a new transaction which has sent out that packet, so we service that quickly so that that transaction is serviced and that transaction is completed within the deadline. Okay, and of course the older packets sort of get serviced later, and maybe few transactions get timed out, right? But what they found out that last in first out is actually the best discipline among those that they tried, in order to keep the success ratio high. Okay. So what happens at the transport layer? So we've talked about what happens at the network layer, at the routers. So what happens at the transport layer? So let's say that A wants to send a transaction to B, and this is the PCN network, payment channel network. So a transaction, let's say, is given, A wants to make a transaction, So what is, let's say A wants to send B a transaction. So what is the transport layer going to do? So it's going to do something a little bit different from transport layer in TCP. I mean, like we had TCP in networks, because TCP just uses whatever the path is available to it. But what we do here is something more advanced, which is related to something called multipath TCP. So A is going to choose K paths to B, and we want these to be disjoint. Okay, so as little overlap between these paths as possible we want, and K is some parameter. Usually you can choose 4 to 8 paths, let's say. And so A is going to find multiple paths. So let's just write that out over here. This is A to B. Let's say we've chosen 4 different paths to B. Okay. Now along each of these paths we're going to send packets. So divide transactions into packets. These are small amount transactions. And these are going to be routed along the K paths. So send packets along multiple paths. And for each path we have a congestion window. And this is the maximum number of packets you can send out which haven't been acknowledged. So what does it mean to be acknowledged in this context of payment channel network? So what we really mean is that these are pending transactions which haven't been completed. Okay. So WP, as we would have guessed, is set based on window increase and decrease algorithm similar to TCP in the internet. So WP is decreased, okay, by some amount, okay, when A gets a marked packet. Okay, so when the destination B tells A that I did get a transaction through, but it was marked along such and such a path. Okay, okay. So mark ACK for let's say for this path. Right. So this means that there was congestion along that path, so I want to decrease the window over here. But what if there was no congestion? Then maybe I can increase this and push more packets through. So there is another parameter alpha, okay, and they've used some ideas from the overall from various TCP protocols. Okay, so they're giving, you're essentially going to consider the window along all paths. So PAB is the set of paths being used for this transaction. Okay, so we said there are 4, let's say, transactions. So you're considering all paths and you're looking at the current window size there, right? And the reason we are doing this is that we have many different windows now. It's not a single window, and this alpha is the maximum amount that I'm going to increase all the windows together if there is no congestion. Okay, so that's the idea, right? And of course, if suppose there was a single path used, then it would just be alpha divided by WP. That would be this, right? But if there are many paths, then I divide by the total window size. Okay, so this is sort of, you can say, this summation over here is the overall window size over all paths. Okay, so why do we divide by W? Why don't we just add by alpha? Well, because in every round trip time in TCP you want to increase by a particular amount. Normally it is 1 packet, right? So you have this funny looking term where you're dividing a constant by the current window size. Okay, but effectively you want the window size to increase by alpha every round trip time. That's what TCP wants. Okay. So alpha and beta are some positive constants. Okay, so this is what Spider does. So it's using ideas from networking. So what you're doing is you have multiple paths from the source to destination. You split up your overall transaction into smaller transactions. So it's very unlikely that a single, instead of having one large transaction which is going to hit bottlenecks and you have to keep retrying and so on, what we are doing here is we are splitting up into smaller packets. Okay, and we are going to send out packets along these multiple paths, and we're going to get feedback. If there is congestion due to which we find out from the marked packets going on any path, then A is going to throttle the packets being sent out on those particular paths, right? Using the formulas which I just showed you, right? But if there is no congestion and all the packets are getting through unmarked, it can increase the window size, okay, on those appropriate paths, right? Right, so this is essentially how the core of Spider, and there are of course other issues to consider. You know, what if 90% of the packets get through but 10% don't, and then there is a timeout? Then what do you do? Right, those sort of issues have to be handled at with other mechanisms. Either you pay the rest of the amount with a new transaction which you initiate, right, or you use some other cryptographic technique that it's an all or nothing scheme, that B cannot collect any money or B can collect his money only, let's say, if all the packets get through, right? There could be some cryptographic scheme for that, right? But anyway, the authors of this paper did a lot of simulations, and they compared their method to other techniques, and you can look at the details in their paper. Okay. So it's an interesting paper with interesting ideas. The question is whether it would be easy to implement something like Spider in the current Lightning Network, because there is already a Lightning Network, and this particular protocol is very different from the current protocol being used in the Lightning Network. Right, here you have ideas of a router and transport layer and so on, which is not there. So ideally you want some technique which is incrementally deployed, which you can maybe only if even 1% of the nodes want to use it, it can be used. Right? But right now this is a radical departure from the current protocol, so it may not be possible to actually use it right away. Okay, but interesting ideas in that you can actually divide a larger transaction into smaller packets and send it along multiple paths, and do congestion control on each of these using the formulas which I showed over here.